This video is going to discuss electron configuration. Hopefully it will tie in information that you read about quantum numbers with the idea of how to locate electrons in an atom. We left off last chapter discussing the model of the atom according to Rutherford, and his model was that electrons are somewhere outside of the nucleus. And in the first part of chapter 4, we discussed that, well, electrons have different amounts of energy based on the work that Bohr did. And so he determined that electrons exist in certain energy levels or orbits around the nucleus. But the work by Heisenberg showed that it's really impossible to determine where an electron is and also to know its velocity. And that's called the Heisenberg uncertainty principle. So we get into the discussion that Bohr's model that we just finished talking about last week is actually flawed in that you can't really know where an electron is. Electrons are not in specific orbits. So we keep going through this same cycle of finding an idea of the atom and then determining that it's not really feasible anymore. And so if we don't know exactly where electrons are, how do we discuss them? Well, it gets a little complicated, as you guys could tell from the reading. And the work of Ernest Schrödinger is really based in calculus and quantum physics. And he came up with Schrödinger's wave equation, as you can see here. You do not need to know this equation at all. But what this equation actually did was use mathematical probability of finding an electron. So Schrödinger redefined where electrons are. Instead of being in orbits, as Bohr determined, electrons actually exist in orbitals, which are just regions of probability where we could find an electron 90% of the time. Think of it as a fly inside of a balloon. If you blow up a balloon with a fly inside of it and tie it off, you know with a certain amount of probability where that fly is, somewhere inside of that shape of the balloon. You may not be able to see exactly where the fly is at any given time, but you are pretty confident that it's somewhere inside of that shape. And so it's the same idea with these electrons. The electrons exist in certain shapes or orbitals, and we'll look at the different shapes in just a moment. Again, it's all based on mathematical probability, and this is our current view of the atom. So we're finally up to date with how we view the atom. Now you've already read about the quantum numbers, and I'm not going to re-teach them here. If you have specific questions, please bring those to class. We're going to focus on really just two of these, and those are the ones that I have highlighted in red. We're going to talk about the principal quantum number and the angular momentum quantum number, and you know the values from your reading. We won't really talk about the magnetic or the spin quantum number necessarily in here, but what these quantum numbers give us essentially is a way to define each of the electrons in an element. And because an element has a unique number of electrons, what we call the electron configuration is unique for each element. So think of it just as map coordinates. So each electron is going to get different map coordinates that exist with all four: the principal, the angular, the magnetic, and then the spin quantum number. So speaking of those orbitals, we're just calling them clouds of probability. So you can see here that there are several different shapes. We're only going to focus really talking about the shapes of the s orbital and the p orbitals. Now these are not solid shapes. These are regions of probability. Think of it as if this were a bullseye and you had thrown 1,000 darts at this target. Where would the dots be? Well, those dots would be in this circle 90% of the time. Now this orbital is called the s orbital. It's spherical. The p orbitals are dumbbell shapes. And with all of these diagrams, if you see the intersection of all of the axes right here in the center, that's where the nucleus is. Remember, the nucleus is a really super tiny, small area, and it's defined here as the intersection of all of these axes. And so if the nucleus is here in the center, then the electrons are somewhere outside of the nucleus, as Rutherford said. However, they're not spinning in specific orbits like Bohr said, but rather Schrödinger states that there's a 90% chance of finding the electron here inside of the shape if the electron happens to exist in an s orbital. If an electron exists in a p orbital, we have this dumbbell shape. So 90% of the time, the electron would be found in either of these two areas. And then 10% of the time, it could be found somewhere outside of that defined shape. Now, after we get past s and p orbitals, the actual shapes of the d and the f orbitals get really complicated, and we're not going to worry about what shapes those are. But you do need to know that s orbitals are spherical and the p orbitals are dumbbell shaped. You also need to remember that, again, this is not a solid area, but rather a region of probability of where we could find the electrons.